Okay. Well, thanks for having me. I'm sorry I can't be there in person. But so what I want to talk today about how we think about reproducibility in the context of AI and machine learning enabled science. And just as background, many of you know that science for the last 15 years or so has been struggling in thinking about whether our results are really as reproducible as we might hope, and it really is a problem across pretty much every area of science. This is a poll from well over 10 years ago from people across many different areas, showing that if you ask people how often have you failed to reproduce an experiment, either of your own or someone else, the majority of scientists in pretty much every area have failed to reproduce a study that someone else has published. This gained prominence, particularly in psychology, with the publication of this Reproducibility Project Psychology back in 2015, which showed that if you took 100 studies published in major psychology journals and tried to reproduce them, you could, if the original study had a significant result, you only got a significant result about a third of the time in the replication attempt, suggesting that, that across many different areas, research is not reproducible. And we haven't had these kind of like replication studies to a large degree in neuroimaging, in particular because of the expense, I think, of doing neuroimaging work. But there's evidence of a lack of reproducibility here as well. And I think this is a nice example. This is a meta-analysis, kind of a re-meta-analysis published by Mueller et al. Back in 2017. Where they looked at previous meta-analyses comparing people diagnosed with depression and people without a diagnosis across a number of different task fMRI paradigms. And each of the original meta-analyses had claimed to have found, consistent differences. But when they put the data all together and fixed some problems with the meta-analyses, they found across those 99 neuroimaging studies, there was no convergence, right? Each of them had reported a significant effect, but if you put it all together, you basically get nothing, suggesting that we probably have a similar type of irreproducibility in neuroimaging. And I've written a bunch over the last decade about what some of the causes of that might be. Today, I'm going to focus in particular on the application of kind of machine learning and artificial intelligence methods and how they might be kind of changing the situation. And so I want to talk about two sort of aspects of two kind of challenges. And the first challenge, when I use the term reproducibility, I often use it in a very narrow sense, which is like just given the same code and data, can I get the same result, right? That's kind of the lowest order type of reproducibility one might hope for. And that's challenging, as we move into AI-based science because of very complex code bases, very large data sets, sometimes that can't be shared, and sometimes immense computational requirements, in the extreme, ones that only companies like Google can afford to actually employ. Now, we know that even in simple situations, computational reproducibility is challenging. This is work by my colleague Mike Frank's group, led by Tom Hardwick, where they looked in psychological science at articles that had been given these open data badges, kind of certifying that they had shared data. This group took those original data and basically looked to see if they could reproduce the results published in the paper from the original data. And they found initially that, the majority of papers had a major numerical discrepancy. Ultimately, without the author's involvement, they were only able to reproduce the target values about a third of the time. And then 24% of the time they could do it if the authors got involved. Occasionally the authors didn't respond. And 28% of the time they couldn't reproduce the original results, even with the help of the original author, suggesting that, that data and in this case, data sharing is not a panacea. There's also a lot of evidence from within computer science that computer science research is not reproducible, repeatable. So this is a well-known study from Kohlberg and colleagues where they looked at about 600 papers from prestigious computer science, either conferences or journals. This is just not even asking, can we reproduce the results, but can we get the code and can we build it and run it? They tried to obtain the code. The code wasn't always shared openly. They were able to get it, some decent number of times. And they were successful less than half of the time in obtaining, building, and running the code. Now, there's a further challenge, which is not just can we reproduce that exact result, but how well does it generalize to new situations like different data sets, different implementations, even different random seeds. And there's a reason to be concerned about this. Now, we know that even outside of AI-based science, there's reason to be concerned about this. We published this result a few years ago where we basically got an fMRI data set, gave it out to 70 different teams, and had them analyze the data and report the tests of 9 different hypotheses. Like, is there activation in a particular region for a particular aspect of the task? And what we saw was that, across those 70 teams, there were 33 different patterns of outcomes. And many of the hypotheses had, 20 to 40% of the teams saying yes. But for any of the hypotheses, there were at least 4 teams that said yes, um, suggesting that, there's a lack of reproducibility, even holding the data constant. We've also been recently looking at this in the context of what we call multiverse analysis, where we take a data set and we systematically vary the workflows. In this case, we were looking at this task that's widely used in the addiction literature called the monetary incentive delay task. And we took that, a single data set, I think a couple hundred subjects, a decent sized data set, and holding the data set constant varied basically 4 different aspects of the statistical modeling and analysis approach. We varied smoothing, motion correction strategies, the particular statistical model, and the statistical contrast. And what we saw was that this is in that monetary incentive delay task in the nucleus accumbens region, which is a region of interest often used in that task. We saw you can get anything from a Cohen's d of positive 0.25 to a negative Cohen's d, negative activation of about zero point 0.1, depending on which particular version of the model you chose. And these are all models that have been used in the literature with this task, again, suggesting a high degree of analytic variability. So how might this impact performance of AI or machine learning models? Well, Joelle Pineau has a great talk from NeurIPS a number of years ago where she looked at how different factors affected performance, in this case of a reinforcement learning model. It's just a model learning to play in a particular environment and obtain rewards. The environment is basically just like a computerized kind of environment where it's kind of going around trying to find basically where it'll get rewarded. And this shows the performance of 4 different algorithms across these different environments. The environments aren't meant to be different from one another. They're all meant to test, performance of these models, but the models show extremely different performance across those different environments, such that even the rank ordering is almost opposite between this half cheetah environment and the swimmer environment between these 4 models. She also showed that if you take a single model, like in this case, this TRPO model, and you take different implementations, in this case, just going on GitHub and finding, different implementations, those different implementations can show radically different performance, again, with even the rank ordering of the modeling of the models changing substantially. And finally, and maybe most worrisome, she showed that even for holding the model and the environment constant, simply changing the random seed could cause substantial differences in the performance of the model. And so this leads you to be concerned that, when you see high performance, you have to wonder, did the researchers just pick a particular random seed that works well? And there's evidence from the literature that this may actually be happening, what we can call accuracy hacking, where people basically try a number of random seeds and take the best result. This is actually work from some colleagues of yours in Milan that's looking at performance in a slightly different area of machine learning, the development of these things called recommender systems, like the systems that recommend videos to you on YouTube. They wanted to know about studies that compared newer neural network models to older approaches. And they found that, less than 50% of the studies had actually a setup that they could reproduce. But interestingly, they found evidence of cherry picking. So for example, they say in our initial experiments, looking at this one algorithm, we found it was competitive at our baselines for only 1 of 3 data sets. Specifically, it was the data set for which the authors had shared the train test split. An investigation showed that the distribution of the data in that specific test set that was used by these authors was very different from what you would likely obtain by just randomly sampling. Look, and that's what they show here, that the test data show a very weird distribution of the relevant features compared to what you would get by random sampling, suggesting that people found a weird data set that gave them good performance of their model. Now, you can do this even with very simple models. This is an example that I worked up where I generated some data sets and or I generated a data set, and then I compared two different classifiers, both of which use random seeds. One is a stochastic gradient descent classifier, and one is a perceptron. And in this case, you see the perceptron does a much better job of that classification problem than the stochastic gradient descent classifier. But it turns out that that's just one of a bunch of results one could get. These are showing y-axis is the perceptron performance, x-axis is the stochastic gradient descent performance for the same data set, simply changing the random seed. And here I took the one that has the biggest difference, the biggest advantage for the perceptron compared to the stochastic gradient descent. But you could equally find a random seed, again, holding the data set constant, that gives you about the same benefit of the stochastic gradient descent classifier over the perceptron. And if you look at the average across all of these random seeds, you basically see that the models are the same. So this leads you to be worried that when you see, performance results in the literature comparing different models, and again, these are simple models. You can imagine this could even be worse with more complicated models. That could just be due to things like different random seeds. We also know that when you see performance of a particular model, you have to worry a lot about whether it's generalizable to different data sets. We've known this for a long time, actually. Tarabla and Efros showed back in 2011 that if you this is for image recognition with neural networks, you take one image data set and then you test on a different one and you got a substantial drop in performance. More recent work by Ben Recht and colleagues basically tried to go out and gather new test data using exactly the methods that had been originally used to generate these large image data sets like CIFAR10 and ImageNet, and showed that when they tested the models on these new data sets across a bunch of different architectures, model architectures, the models all showed a large drop in accuracy. The black dashed line is basically what you would expect if they show the same accuracy on the new data set as the old one. This shows that basically all the models show a substantial drop. The rank ordering is pretty much the same. So the best models on the original data set are also the best models on the new data set for the most part. But nonetheless, the overall accuracy goes down quite a bit. So I sometimes joke, if you look at machine learning papers, there's this trope of people putting the best performing model in bold font. These are just a few examples from the papers with code SOTA state of the art listings from about a year ago. And you see that, the best performing model is in bold, and it's almost always our model, the one that we're trying to tell you is the best one, is the one in bold, of course, because if it wasn't, then we wouldn't be able to publish the paper, because the goal of the paper is to say, hey, we did better than everybody else. But it starts to seem like this is sort of the equivalent of, p less than 0.05. And just as we know that there's a lot of problems with p hacking, such that people try a lot of analyses to find p less than 0.05, similarly, you can imagine that those same types of problems go on here. Now, there's another elephant in the room in machine learning-based science that we know has substantial effects in driving bias, and that's what we call leakage. And the idea is that when you fit a machine learning model, the idea is that you should fit it such that the training data are completely independent of any data that you're going to be validating or testing on. Usually we'll do cross-validation where we split the data into parts, train on one of those parts, test on another part, and then often the gold standard is to have a held out test data set that you then go kind of test your final model on. But leakage is when, due to various things that I'll talk about, the training data gets contaminated by the validation or test data. And Kapoor and Narayanan had a nice paper a few years ago, basically showing that across many different parts of science, people have found that there's evidence of leakage as one of the pitfalls of application of machine learning based methods to scientific questions. I'll just show you a couple of examples. This one is from actually from genomics, looking at 55 papers, 99 model results, and basically finding that about half of the papers used feature selection methods that can often lead to data leakage. So let me show you an example of that. This is an example from neuroimaging, a paper that had published, claimed that they had basically people from three different groups of mild cognitive impairment, and they used diffusion imaging and did classification using support vector machines to try to discriminate between these three subtypes of mild cognitive impairment. Now, when somebody tells you they have 97% classification accuracy, especially with sample sizes like 18 and 13 and 35, you have to be very worried that something has gone wrong, especially for something as subtle as different types of mild cognitive impairment. Um, so what if you look at the paper, what you see is they describe their method. The analysis included two steps. In the first step, we performed a feature selection. The rationale behind this step is that not all voxels discriminate between groups. The second step consisted of an actual classification for each comparison using the SVM algorithm. So it sounds like what they did was they first found the voxels that discriminate between groups, and then within those voxels did the classification across all the groups. Now that's problematic because we know that, in fact, on the right, this is a simulation that I ran of what happens when you take data of roughly the size they have, where there's no actual signal, no difference between groups, just generate random data with no difference between groups, and either do feature selection within cross-validation like you're supposed to do it, or outside of cross-validation where there's leakage of the test data into the feature selection. You can see that you can get like 97% accuracy doing feature selection outside of cross-validation when the true answer is basically no accuracy at all, 0.5, because the data are just generated randomly. And this actually was pointed out by Dicchiotti and colleagues in a commentary on that original paper about what they call peaking. Some people call it leakage, some people call it peaking. Here's another kind of very prominent example that came out a couple of years ago regarding a paper that had been published back in 2017 using machine learning methods to analyze fMRI data and claim to identify suicidality. So this is an image from the press release where they show this supposed brain activation pattern for the word death in people who had made a suicide attempt compared to control participants. And this group got a $3.8 million grant to diagnose suicidal thinking. And it turned out that this paper was subsequently retracted after another group of researchers looked more closely and found that, in fact, they were doing the same thing. The features of the classifier were tuned to that particular data set, not in a way that held out the test data. And so we know that this is a problem. In fact, there's a paper coming out in one of the psychiatry journals very shortly that will show that this is a big problem in some of the psychiatric prediction literature as well. Now, another place that we've recently learned that this can happen is in basically the modeling of confounds in machine learning data. So often, you have a data set where you want to do classification, but you also have a bunch of confounding variables. And one common thing to do is to do some kind of confound regression across the entire data set and then go do classification on that confound regressed data. And what this group led by Kashtu Patil found was that if you do that across the entire data set, you can get leakage, what they call confound leakage, that can give you, in this case, so here this is the original data. The blue is the kind of the non regressed data. The red is the regressed data, showing that when you do the confound regression, you get much higher, you get almost perfect predictive accuracy. But you get that even if you shuffle the label, such there should be, for the non-confounded, non-regressed data, you basically get zero accuracy, like you should, because the labels are variable are randomized. But even with even with randomized labels, you get almost perfect prediction with due to this confound leakage. Um, Another concern here has to do with sample size. We've seen, very often classification or prediction results, based on very small samples. And we've known for a number of years that small samples give you highly variable predictive accuracy results. Gael Veracruz showed this in his 27 paper. And we think that in the literature more generally, one of the main causes of a lack of reproducibility is the use of very small samples. Tal Yarkoni pointed this out back in 2009. So how do we improve these issues? So Veracruz and Trepligina had a paper a couple of years ago that laid out a number of things that I think are important. The first is to really safeguard against leakage by having a separate test data set that is just like in a lockbox. You don't touch at any point until you actually start, you have done all of your modeling because you want to make sure that your results generalize to that test data set. Um, Document how you've gone about doing any kind of hyperparameter selection, including selecting your model, feature selection, anything like that, based only on the training data set. So again, really making sure there's no leakage. Having sufficiently large data set, obviously this depends on the nature of the problem, but they recommend at least several hundreds, if not thousands, ideally. And I think that's what, in the imaging literature, based on the work from a couple of years ago by Marek and colleagues, we're coming to realize that, in many cases, any sort of like correlational analysis between, phenotypes in individuals and brain imaging data often requires hundreds to thousands of samples in order to become stable. There should be confidence intervals on the reported metric based on, resampling, and a discussion of the variability of the results due to arbitrary choices like random seeds and due to the data source. Or is the data source really, how well can you, even if the results are real for that data set, how well can you generalize to other data sets? And then they also point out that, we need to be concerned when, as in the machine learning literature, you often see methods with the bold font where that number is just, a couple of, a fractional bit better than the existing benchmark. And the question is whether like a method that just gives us a tiny improvement in performance, especially if it's being compared to a much simpler method, whether that's really something that we should be paying attention to. So I was involved in a project called Reforms that also generated a set of reporting standards for science that uses machine learning and artificial intelligence methods. This was published in Scientific Advances last year, I think. And if you go to this reforms.cs.princeton.edu site, you can find a checklist that you can use if you're working in this area to basically go through and make sure that you have documented everything in the paper that one needs in order to fairly evaluate this kind of work. Now, I've talked a lot about kind of, what, sort of like models like, neural networks and things like that. But obviously, there's a lot of interest right now in large language models. And so there's a whole other interesting set of reproducibility challenges that come out in the context of large language models. Primarily the fact that these generative models are inherently stochastic, right? That unless you do something special, you're never going to get the same answer twice. Now you can do special things like in many cases setting the random seed for the model, or at least for the inference part of the model. And this on the right shows like in GPT-4, if you just go to it and say output a random vegetable, these are the results. If you don't set the random seed, it says broccoli, carrot, cabbage, cucumber, cauliflower, spinach. If you set the random seed to a particular value, it always says the same thing, right? You can also turn the temperature all the way down so that it always gives you exactly the like kind of the most likely answer. You don't always want to do that. But another problem is that these commercial models can change without warning. Like, GPT, OpenAI can change the GPT-4 model without telling you. Now, you can generally get what we call a system fingerprint. And anytime you're using these commercial models for scientific purposes, you should be, tracking the fingerprint. But the problem is you can't always get back to the old fingerprint, so that the results are going to be inherently irreproducible. Now, one way to fix that is by using open source language models. So increasingly, one can obtain access to models either running on your own machine or running on a commercial provider that provides access to these models that allow a much greater degree of reproducibility because you can get back to exactly the same version of the model. You can set the random seeds, and this allows you to be sure that you can go back and reproduce the results of your particular analysis in a much more robust way than you could using the commercial large language models. Okay, so I think I've hopefully convinced you that there's sort of a looming reproducibility crisis in AI and machine learning, and that reproducibility one requires both sharing of data and code. We need to be able to have access to the code and the data, but that there's also a number of other best practices that can help us improve reproducibility. And I will stop there and take questions.
Thank you very much, Russ. That was very clear. In fact, what you said, you anticipated the question I had written down, so I leave it to someone else to start shooting a few questions. Please open your camera so that you can appear. Don't be shy. We have 31 participants. Marco, Laura, Lucia, and so forth. I will try with one question. So you touched the very interesting aspects of the problem. As a last point, you touched one of the large language models, which are in the hands of a simple user. They seldom give the same answer, even to simple questions. So can you reiterate what would be the strategy to make sure that such models contribute to assess the soundness of your data and eventually the reproducibility?
Yeah, all right. No, that's a good point. So with regard to large language models, if you're going to be using a commercial model, then the one thing you want to there's two things you want to be able to do. One is you want to know how variable the results are. So if you're claiming that some result is true based on the output of a large language model, you want to make sure that if you run the model 20 times, which you can do easily using the API, like I did with the vegetable thing, if you do that 20 times, what's the distribution of answers, right? You can also, if you really want to know, if you really want to get a single answer, the easiest way to do that is you can usually control what's called the temperature, which is sort of like the degree to which the model explores different solutions. If you turn the temperature down to 0, it's always going to give you the most likely answer rather than sampling from a bunch of likely answers. Sometimes you might want that, but sometimes you may not. You want to actually know, because it might just be that best answer is only slightly better than the second best, and you want to know what's the range of possible answers. So those are the two strategies. But I would say that if you're doing science, generating results that are going to be used from a large language model, you probably want to be using an open source model where you know that you can reproduce the results from that same exact model. You can do the same strategies there of random seeds and temperature, but then you also will always have access to that model.
Now, more questions. I have a second question, then I'll leave it to others. Talking about data leakage in supporting vector machine analysis and classification, what would be in terms of data how good would it be in terms of data leakage? I suspect very bad, to use the univariate group analysis as localizer, then to explore subsequently the classification power within those areas identified by the univariate analysis. Would it be bad?
If the univariate analysis is based on the same data that you're doing classification on, that's basically what that paper did that was retracted, the suicide paper. Yeah.
Yeah, it was a suicide paper in that respect, because they used the wrong classification strategy. So what is predicated essentially is that totally independent data should be used for to identify, to clarify, or to identify a subset of brain regions, like an independent meta-analysis, for example, could be a good one, I guess. before trying to use classification strategy. Is there any manuscript with sort of the 10 golden rules, sort of kind of manuscript that makes a suggestion and makes practical cases? I'm asking for the audience and also for the non-specialists that could
Yeah.
be.
I mean, I think that the Veracqua and Cipollina paper that I cited is probably the closest you will get to that. But Veracqua's 2017 paper, it was called Cross-Validation Failure, also is like another version of that. There's not like a 10 simple rules sort of paper. Somebody should write that. But those are probably the two I would point you to.
Okay. More question, please.
Hi, Ross, and thank you. Maybe I go. It was very interesting, but I had a feeling when I saw this slide of yours was giving the advices, no, improving machine learning reproducibility, no, and rightfully you stressed a lot about one problem. It is leakage of information. That is very important, totally important, and I fully agree with you. But on the other hand, well, this is one thing that whenever you start to use these kind of tools, it's one of the first things that you need to realize. Otherwise, I mean, in any lab, this is probably the first thing that they tell you. No, look, you need to be very careful in not mixing the information between these two steps. And so, I was wondering how come that you need in 2022, you need to say this thing again that I mean, it's quite some time nowadays that machine learning methods are around. So, I mean, the community should be more or less aware about the severity of these errors, no? And on your shoulder, on your feet, not on your shoes, you may say that you may have a feeling that you are trying to empty the ocean with a spoon, because I mean you kind of repeat the same good advices and people don't learn. So
Yeah.
maybe I was wondering whether you have an idea of why there seems to be the communities or sub-communities that are making more or less similar errors over and over. I mean, at the end of the day, the super famous voodoo correlation is not different from data leakage. No, we already discussed that a long time ago. So why this thing is reproducing?
Yeah. I mean, so that's a great question. I think part of it is that there's just a lot of people. The tools are so easy to apply now that people who haven't learned those lessons, even take the tools, use them, see a result that looks great, and move forward with it without asking. So I think there's really kind of a meta-scientific question here of why aren't people questioning their own results, right? And we had this kind of philosophy in the lab, like if you get a really good result, you should start by assuming that you probably did something wrong, right? Because when you get a really bad result, that's the same assumption you often make, right? And so, but a lot of labs, students, there, and so in fairness, there's a lot of pressure to publish, right? And to publish in fancy journals, you need to have really clean, nice results. So I understand what drive, some of the incentives and pressures that drive people to do it. And I think that, the tools have made it so easy in some cases to apply these things that one doesn't have to know very much. One doesn't have to have read a lot of literature to go apply this stuff. And so, my hope is that, even if I can't get people to stop doing it, I can at least get people who are going to be reviewing the papers to be attentive enough to it that when they see those papers, they'll ask these questions.
I will try to ask a question. So thank you, Ross, for the great talk. That was a lot of talks, food for talks. And I wanted to ask you a comment on a related issue, because I think reproducibility in this field is important and is also a necessary prerequisite for interpretability of the results and of the analysis. And a very well-known problem of machine learning and artificial intelligence is that these kind of algorithms very often lead to results that are difficult to interpret, or some decisions are difficult to interpret and know exactly on what they are based. And so I wanted to hear your take on that, also because of the issue of selection bias you were talking about. I think that especially the generative AI algorithms are stochastic, as you said, and it's very difficult to understand the kind of process that are underlying these kind of decisions. And even in those cases where methodologically and technically the researchers are doing everything right, everything correct, they're not biasing their selections in any way. I wonder whether from a human cognitive bias, we are not maybe taking some choices, some decisions that are a bias in itself and may lead to some particular conclusions as opposed to other ones. If we're not losing an opportunity to use AI in a better way, in a sense.
Yeah. Yeah. So there's a lot of interesting questions there. Let me go back to the beginning. So I think that, so with regard to interpretability, you're exactly right. The models, people often refer to them as black boxes, right? Because there's a couple of issues there, right? One is, it gets back to this, longstanding question about the goals of science with regard to, understanding versus prediction, right? If all you care about is predictive accuracy, then it may not matter whether you can understand the thing. But I think it often does, in part because you want to know, are you predicting based on like some kind of confounding thing, or are you predicting based on something that is going to be generalizable, right? And there's a bunch of techniques for trying to do this, like kind of explainable AI, kind of understanding how the models are working. We had a paper a couple of years ago in Trends in Cognitive Sciences that showed how these different versions of these methods can actually give you pretty substantially different types of answers. So it's not like there's one explanation for what's going on. And then again, right, you have to worry about the degree to which there might be confounds sort of driving things. Like, what are the features? If you see that it's like just the ring of the outside of the brain that's driving that's where all the predictions coming from, that's going to lead you to be concerned, right? Regarding the use of like generative models, I think it's really hard to know kind of what we're doing to ourselves right now. It's funny, I'm actually writing an online book right now particularly about like AI assisted coding and its role in kind of reproducibility in science. If you go to my Substack, I've been kind of like rolling the book out slowly there. But I think there's a ton of interesting questions about like, how we need to be thinking about doing science in the context of these models, either for generating code or for generating, if you want to treat the models as like model organisms, look at their behavior or use them to analyze data. And I think we just don't understand what kind of biases might be getting embedded, in those models in the way that you're talking about. I think that's something that a lot of work still needs to be done on.
Thank you.
Sarah Palermo wants to ask a question. Hello? Maybe not. A related question, Russ. In a different talk that I saw on the YouTube, you are treating the issue about how much artificial intelligence is reliable in writing code that is useful in analysis of psychological data or in fact, even fMRI data. What is your take now? Because your exploration was based on GPT-4, if I well remember.
Yeah. So if you look at the book that I mentioned, and I'll send you the link that you can pass around to folks. And actually, I have a newer version of that talk that I just gave at Neuro Academy that I think is online that goes into the latest models using Claude Code and some of these agentic coding models. The models are really good at generating code that works to solve problems, right? The question is whether they're always solving them in the right way. And so, I often like to say that in some ways, coding is kind of like the best case scenario for the application of AI in science because you can always write tests for your code to make sure that the model is doing the right thing, right? If you know what the requirements are, here's the answers it should give, here's the things it shouldn't do. You can generate tests and make sure that the code does all that. And then once you show that it does that, you can kind of accept it as solving the problem as well as you would have solved it by writing your own code. Um, Having said that, it's the models. The biggest problem is that the model, like Claude. There's been this joke on. I had a thread on Blue Sky recently. This joke that Claude Code very often says, "You're exactly right." And then it'll say, "I've solved the problem," when you're not right and it hasn't solved the problem. And so the models just don't have good insight into when they've actually solved the problem. They'll often end up like going in circles. So my book, or at least the draft sections that are up there so far, talk a lot about like, strategies for using the models to do a better job of actually solving problems. I think it's for my concern isn't so much the reproducibility because again, you can create the test and make sure that it does the right thing. The strategy is really like making sure one that people know how to do the test, and there's a whole chapter on that, and then realize that when the model says you solved a problem, you haven't necessarily solved the problem, and realizing that you need to like watch what it's doing and make sure it's doing the right thing.
Daniele?
Thank you very much for your wonderful talk. And I have a very confused question, so I'm sorry already now. I was wondering how much the results that you presented reflect somehow the immaturity of machine learning and AI, in the sense that we are still developing the models to do that. I mean, we apply the models that computer science is developing, but it's still developing these models more or less every year come out a completely new model to classify and doing this stuff. So how much this problem of replicability and reproducibility reflects the fact that that we are still working on the basics of these models, so we still don't know if they work at all.
Yeah, that's a great question. I mean, clearly there is an immaturity, and you can kind of attribute some of this to that immaturity. The points that are being made are not new points. I mean, there's a paper from this guy Kopas in like the early 1980s talking about. I mean, he called it shrinkage, the idea that when you fit a model to one data set, you're basically fitting both signal and noise, and then it doesn't necessarily generalize to another data set. That wasn't so. And then when people early on doing cross-validation talked about these sort of problems. So it's not like these are unknown problems in computer science. I think that it's almost like every field has to reinvent the wheel, right? Psychology, people have been talking since the 60s about the problems of p-values and p-hacking, but we had to reinvent that in the 2010s when we realized that stuff was going on just by using different terms. So I think it's part of it is just goes back to this problem of incentives, right? That in the CS literature, the incentive is to get your model to be in the one with the result in the bold font, right? And so you're going to do everything you can to get there. And sometimes if you don't realize it's the wrong thing to do, or just inadvertently do it, or do it on purpose, that is going to result in bias. I think so. I don't think that the field can get off so easy by saying, "Oh, we're young, we just learned about this stuff." I mean, people, Joël Pineau gave a talk in 2018. That's 7 years ago. So certainly there's been time, and there was a whole NeurIPS workshop on reproducibility in machine learning in, I think, 2019. So people in NeurIPS, the main machine learning conference, have been talking about that for a long time.
More questions? Last question from me. I mean, we grew up with analytical packages that were all human-made, okay, and which concatenated a series of operations. Do you think we will get to AI being able to produce an entire suite of applications that can solve complex problems, as we did in the past for imaging data, from data acquisition down to maybe data interpretation.
Yeah, I mean, in fact, those already exist. So there's, for example, there's a thing called Deep Prep, which is meant to be like a deep learning based version of fMRI prep. People are working on basically like, deep learning based versions of FreeSurfer, like this synth strip, like, various early, some of the subsets of that. So people are certainly working on trying to develop, basically taking all the stuff that one of these big workflows does and just have a complex neural network model learn it. We had a paper a few years ago. I had a grad student who was working on the idea of basically building deep learning based analytic workflows that basically learn the best workflow. Like, each layer in the network is doing, brain extraction or connectome modeling or confound modeling or whatever. And with enough data, you can, in theory, learn rather than having to try all those different modeling approaches and see which one gives you the best result. You just use gradient descent to learn the best pipeline for a data set. And that turned out to be really hard. He finished his PhD without really kind of solving the problem, except for a proof of concept. But no, so there's people certainly want to do that. The question is, would we trust it? Like if I gave you a black box and said, hey, this thing can do as well as FreeSurfer, but it only takes a tenth of the amount of time, would you trust it? I'm not sure I would for our work yet.
Yeah. One last question, Daniele.
Yeah, thank you. It came up to my mind that I read a paper this year that came out this year about evaluating how, after 10 years of reproducibility crisis in psychology, things have changed. So this paper basically look at how many fragile p-value have been published in different subfields, the median effect size, the sample size, and actually we got better. There are signs that all the emphasis on this crisis of the needs of power analysis actually improve the quality and the reliability of the results. Do you see a similar path for AI or also in imaging data for having this kind of positive trends?
Yeah, I mean, I think that you just need the field to pressure people to do it, right? That's what had happened in psychology. Journals started pressuring people to pre-register and to use power analyses and all this sort of stuff, and it had a substantial positive effect. I think that the reviewers of papers basically need to do that. Now, there's all these other questions about the nature of the review process in CS conferences. And the gaming of the system in those conferences, and there's a lot of problems there that I think we don't have as much in the kind of the journal publication sort of approach that we use. And so I think understanding how to get there is a big question. I personally feel like there are cultural problems in CS around these conferences because everybody, people are just, because of everybody's so deadline driven and they're pushing so hard that very many of the papers that get submitted are basically like, this is what we could get done by the deadline, and I think aren't kind of as well thought out as one might hope. And so there's interesting conversations to be had there.
Yeah, we have one final question, I guess. Lucia?
Yeah, hi, thanks again for...
You should open your webcam.
Sure. Sorry. Hi. Yeah, I just like to ask you for maybe a comment, which is more related to the neuroimaging field than for machine learning itself, because maybe it's an issue related to what we were discussing now, is that if you publish anything related to neuroimaging nowadays, you are basically asked to run some kind of machine learning analysis, even on data sets that were not meant for that. And you very nicely explained that today, that in order to for these models to run properly, you need, for instance, hundreds of observations, and most of the time in task-based fMRI dataset, you don't have so many observations. So one question could be, how can we, in a way, sensibilize or spread the voice to reviewers on the fact that we don't necessarily need to apply machine learning, because otherwise I think this creates noise, because you're forced to use these algorithms where they are not meant to. And this is an issue. Probably some of the wrong habits that we see now in published papers would not be there in the idea of the authors. I don't know if you have any comment or suggestion on this issue.
Yeah, that's a great question and point. And it is certainly the case that, I mean, I have a continual frustration with reviewers who insist on trying to rewrite people's papers, right? I think that the goal of review should be to tell me what the concerns are about my paper, and then don't try to go tell me that I need to go do analyses, unless it's the case that, I mean, the place where that kind of comment is appropriate is if you're making a claim that requires, kind of a real predictive model with out of sample prediction testing to be able to establish that claim. If your claim doesn't require that kind of evidence, then it's totally inappropriate for a reviewer to ask you to do that. So I think that the way to push back on that is basically to say, look, here's the scientific claim that we're making. This claim is not advanced by those additional analyses. This claim only requires that we show that this particular effect exists. We didn't plan those additional analyses, and so it's not appropriate to go do them, simply for the sake of doing them, unless the claim really requires that result. That would be my approach, I think.
So, because we have touched this subject, I have one last question myself. Is classification substituting quantitative reverse inference at all? Because this is usually the issue and the question that reviewers ask. If you make an observation, forward inference based on experimental design, and then you try to add some kind of face validity using quantitative reverse inference, then the reviewer comes up to say, no, you should have run a classification experiment in which you demonstrate that by using supporting vector machine or something of the like, that particular area of the brain really discriminates between two alternatives hypotheses. So the question is supporting vector machine or classification in general substituting quantitative reverse inference at all?
Well, I think it's sort of. So, I mean, yes. So classification analysis allows you to quantify a particular scope of reverse inference, right? So the problem, it's like when people talk about reverse inference in the literature, like when I wrote that original paper, the problem was people would see activation in the anterior cingulate and say, oh, that person must be experiencing conflict. Or they see activation in the amygdala and they say, oh, that person must be experiencing fear, right? And the question is, do those activation patterns support that claim, right? So the clearest way to do that, right, is if you have data from that person experiencing fear and from that person experiencing conflict and from that person experiencing other things, then you can say, out of this set of possible things, we can show the evidence that they're actually experiencing fear or conflict or whatever, right? But that only helps you within the range of things that you looked at, right? So people often want to use like neurosynth to say, across the literature, how strongly is this pattern of activity associated with particular terms in the text? And that's another way to do a different kind of reverse inference. It's a much broader reverse inference, right? But it also is problematic for a number of reasons. So they're both ways of getting at the question of trying to infer what the processes are that are going on in a person's head. One is kind of more precise but narrower, which is building your own classifier. The other is less precise but broader.
Right. Because my objection would be that by narrowing the number of possibilities by classification, you may have the illusion that you are exactly mapping an isomorphic process to the one that you want to interpret, especially when you're dealing with, say, in quote, associative brain areas. I mean, there would be really very little possibility that one brain area contributes to only one or two processes. So demonstrating that the same brain area may classify among two classes of possibility doesn't necessarily demonstrate any better than a quantitative reverse inference, the fact that there is an isomorphism between the processes you are trying to characterize with forward inference and your classification.
Yeah, particularly because there could be confounds, right? What if there's just a task difficulty confound and that brain area, turns on more for difficult tasks in general, right? The fact that it turns on for the same thing that you're doing, sorry, the fact that you say did it in a working memory task and get that area and then want to claim, oh, the person's engaging in working memory because look, we can decode, our task from that area that is involved in working memory. It might be involved in 20 other tasks, right? So that's what I meant by kind of the narrowness of the scope. Yeah.
Okay. So if we don't have more questions, we can thank very, very, very much Russel Poldrack for his contribution to NeuroMi